You gotta know a day.
Today we're going to talk about the Davisson Germer experiment, where they showed that electrons, not just light, acts like waves. It's called the wave-particle duality. We've already shown that that electrons act like particles. Now they showed that particles act like waves. This is the apparatus that they use. They shot electrons through a little electron gun at a nickel crystal. Yeah, you can make crystals out of nickel. And it diffracted off and went to a detector. That detector was called a Faraday box or a Faraday cup. And they found that the angle that worked best, and this detector actually worked on kind of an arc, so they could see where the biggest peak was. And the biggest intensity peak was at 50 degrees, this angle here, and where it was shot out at 54 electron volts. Let me tell you about de Broglie's hypothesis. This is our boy, de Broglie. And he knew that light waves, if you shoot them through narrow slits, will show this diffraction pattern because of interference between the light. So this is what light looked like. You shoot it through here, you get a detector, we see light and dark bands because of interference, like waves that overlap. And particles, if you shoot them like this, will just go through and hit their detector. But electrons, he thought, are like light waves, so if you shoot them through, they should show the same sort of pattern. It's true for light, it must be true for electrons. Well, they supported it. Let me tell you a little bit more. Let me tell you about Bragg's law too. Bragg's law relates the wavelength of a particle or light, any wave, to the distance between. So this d is the distance between. This is the wavelength. And the 50 degrees that was measured actually agreed with Bragg's law. In fact, here's a little bit more math fun. I'll talk a little bit about it. They did the experiment. They found that 50 degrees with this 54 electron volts, in theory, it should have, because of de Broglie's hypothesis, had a wavelength of about 167. Well, they did it, and they measured the d, the distance between them, times the sine of 50 is 1.65 angstroms. They like to ask about this question, or in questions, they like to ask this 1.65 angstroms. They see a big peak. This is the graph. They shoot it. They see a big peak at 50 degrees. Something else to know, de Broglie's hypothesis, he said it in 1924. They did this experiment in 27, and he had his Nobel Prize in 1929. That is wild. 3 years to experimentation, then 5 to get the Nobel Prize. Pretty darn cool. And really, if there was diffraction, the only way for there to be diffraction to get a wavelength is for this to be true, which is why it supported and proved de Broglie's hypothesis. But the wavelength is actually related to Planck's constant divided by the momentum. The only way you could get this pattern and this length is if they were actually waves.